Dan. You just joined in time for our technical workshop at CrowdStrike. I guess my colleagues also handed you a quiz that we're actually going to do a raffle on the 5th of July. It's a technical quiz, so take your time. There are some interesting technical questions. And okay, now back to this presentation. The idea is that it's not necessarily coding workshop. First of all, I'd like to raise the developers in the audience. I'd like to raise your hands. Who's a developer? Okay, so quite a lot. We're not necessarily going to have a coding exercise. This isn't the purpose. Mostly it's an architectural kata, so that we're going to clarify all these words here, like stream processing at scale. And we want to engage you into our workshop, so we have a lot of swag that we are going to give away for each of and every one of you that's going to get involved. Also, don't forget to check out our booth. It's on the first floor in the Transylvania room. And then you can find more details about us. We're an awesome cybersecurity company. Okay, so now with the agenda, we're going to have a small intro about ourselves. We're going to see about the impact that CrowdStrike is having and it's protecting its customers. Then we're going to have an overview of what we're going to do in the workshop. So if you don't know cybersecurity, the workshop isn't about cybersecurity. It's mostly about big data and how we do big processing at scale. We're going to have a live demo. We coded an application just before the workshop, so please bear in mind we're two engineering managers. We had to do some peer reviews, so it might have bugs, and we pray that the demo gods are going to help us and we're going to have a successful demo in the end. Finally, we're going to debate on the architectural decisions that we made for this cloud solution, and we're going to end with a conclusion. Okay, so without further ado, my name is Cezar. I'm an engineering manager at CrowdStrike. I have over 12 years of experience in multiple technology stacks. I started with network testing, done some web development, and after that I've joined this awesome company, which is CrowdStrike, doing data-intensive applications, like I said, that I'm really passionate about. I've also made the transition to an engineering manager role, and in this position I lead a team, and I am helping them, empowering them to innovate and develop great solutions. More on that, on the CrowdStrike culture, I'm going to leave it to Dan. He's also an engineering manager, so Dan, tell us a few words about yourself and the company.
Thanks a lot, Cezar. Compared to Cezar, I have much more less experience in the engineering field, but I'm fresh engineering manager at CrowdStrike. But during my experience as an engineer, I worked a lot with scalable and distributed systems. I learned a lot, I applied them a lot at different positions, and for the last 2 years and I think 4 months, I'm working at CrowdStrike, and I'll probably work for life here. We can explain later why. And one of the main important things at CrowdStrike, we focus a lot on people. As managers, we tend to help them to grow, to tend them to achieve all their goals in record time. And as well, one of the key values of a company is promoting the leadership at all the levels. So you are your own manager, you decide what you do every time, and it is great. Our role as an engineering manager is more to guide a person, not only to monitor it, to tell a person what to do, and to micromanage everything. So, more about CrowdStrike. CrowdStrike is a cybersecurity company who offers B2B products, and according to the Forrester Wave, CrowdStrike is actually the leader in the field. The company was founded in 2011. It's a cloud-native security company. It's one of the first, I think, if not even the first cloud-native security company founded in the world. And it's a remote-first company since day one. We have people across the globe in different continents, in different time zones, and we tend to have a really deep cover and don't discriminate on the people's location. And the main goal of CrowdStrike is that we stop breaches. So what we offer to customers is that we help them to not leak their data. How it's manifested, it's usually we stopped more than 60 5,000 of potential intrusions, which is quite a lot, and you can imagine what amount of money we save to our customers. We ingest in our cloud system over 1 trillion of events per day from the customers' sensors. 1 trillion, it's 1 and then 12 zeros. I don't have enough fingers on my hand to represent those. So about our cloud and how we process this amount of big data, we use Kafka intensively as a streaming pipeline. We have a lot of different Kafka clusters deployed in different clouds. We use Cassandra and Elasticsearch as our main persistent storages because those scales a lot. We have a lot of Cassandra clusters, a lot of them with 480 nodes, so you can imagine what is the amount of the data we store, amount of the data we keep every time. We have Elasticsearch clusters with up to 100 and over 100 of nodes that are scaled and maintained by our infrastructure engineers and data services engineers. We use Redis a lot. We use Golang as our primary language. We use other languages as well, but we'll explain later why we choose Go. We rely on a lot of solutions from AWS, and almost all our deployments are in Kubernetes. What's important is that right now we have more than 300 microservices. We have tens of petabytes of data that are processing day by day. We have a lot of machine learning in all our algorithms, in all our detections, in our execution in cloud and on the sensors. And we have dedicated security researchers and threat analysts that are working day by day to protect our customers. A little bit about CrowdStrike Romania now. CrowdStrike Romania was started as a thing in 2016, and then in 2018 we opened a research and development center in Romania. We have people from Bucharest, Cluj, Brașov, Iași, and a lot of other counties, a lot of other cities. We have people in roles of cloud, data scientists, SRE, security researchers, software development engineers in testing, UI, design, and so on. We have full ownership of our products. You build it, you own it. This is one of the concepts at CrowdStrike. And right now we have, I think, more than 170 employees, and we are still hiring. We have a lot of positions for different levels, so feel free to talk to us at our booth. We can present everything that we are actually doing, and maybe you can be interesting to join an interview with us and have a discussion. So, to our workshop. What to expect from this workshop? As Cezar mentioned, it's more of an architectural kata. We're not going to have physical coding due to the time limitations and due to the room limitations. We'll look how we can improve and inspect our architectural decisions, how we can improve it over time, what are the lacks of a proposed architecture. And there are some disclaimers, as mentioned. It's also not a Golang tutorial, despite we love this language. We can recommend you later, and we'll include some of the slides where we show you why we love it and why it's very good language. So back to Cezar now.
It seems that mic still wasn't working. Yeah, so first of all, I'd like us to have a glimpse of what the tools we're actually going to use when doing this practical exercise. So dealing with large amounts of data, we're going to start with the free observability pillars. It's very important for us at CrowdStrike to have an overall view of the data that we store. So we're using Grafana to have meaningful dashboards regarding our data. We're collecting data with Prometheus and Graphite. Graphite is the legacy system for this, in this regard. Splunk plays a key role in log management, so we're basically using it for collecting all logs from the microservices that we use. As Dan stated, the bread and butter of our processing and indexing and querying pipeline resides with the Golang microservices. We're using Kubernetes deployment, so essentially also in regards, every time we do a commit, and it ends up being a Docker image, we're also using Jenkins pipelines and Spinnaker to do the effective deployment in our environments. Now, in regards to the data persistence layer, we're using Kafka for ingestion purposes, and as we will see when describing the application, because we're going to do a lot of aggregations and searches, we're using Elasticsearch. This fits very well for our use case. I'm not sure how many of you are familiar with Elasticsearch or other document store. I don't know, MongoDB. There was the MongoDB guys here, so can you raise your hands? Okay, so quite a lot. So this is going to make it very interesting. Maybe we can explore some other alternatives that we thought of. Also, we use Redis, as we will see, for some progress tracking jobs. Redis isn't very known necessarily for the durability. But based on the workload that we actually use, we make trade-offs between Cassandra and Redis. Also, when it comes to compute, our Kubernetes deployments are running essentially in AWS. We also have some of the persistent layers that are still running in AWS, but as a long-term solution, we plan to migrate and use most of the services into data center deployment. Okay, so I guess now we can see the application that we're going to do. So like I said, don't worry that you don't know cybersecurity. How many of you have heard about the Rotten Tomatoes? Okay, so this is Crowdy Tomatoes, from CrowdStrike. Yeah, so this doesn't necessarily mean that the data is accurate, right? So we're gonna see why. It's essentially a movie rating system. So like any cloud-based system, we're exposing a crude API, so we can add movies, we can explore the movies that we added for doing the tests. Also, something really important, ratings are randomly generated, and I'm not sure, do you guess why we're doing this? Maybe it's somewhat obvious. Ideally, we wouldn't like everyone in the room to actually start generating data because we wouldn't be able to generate data. So what we're actually doing, we're basically multiplexing one rating request into several other requests. So we have also a dedicated API for this. Dan is also going to highlight this. So we're generating a lot of data, we're indexing it. Then the next step is to explore the data that we have. So we're using Kibana. We're going to use a Kibana dashboard for that. So it's a time series like data. And like I said, we need your help into submitting meaningful data to our system. Okay, so we can go further. Okay, so before we continue and we deep dive into the system architecture, if you have any questions or if you want to start a debate, we're open to do this every time you open. So just please raise your hands. Okay, you have a question? Okay. This is an improvement. So the question was if we're using horizontal pod autoscaling. So the answer is no, but it is something that we added as an improvement because we're going to have an improvement page, right? Because this is mostly based on the load that we're actually going to be supporting. Okay, so if we look as a system bird's eye view for our architecture, we have 3 different major components where we have effective Golang code. So we have the Crowdy API, which is running on Dan's machine. So we will share the IP where you can explore the API, so you can connect to Dan's machine, so please don't hack it. Okay, then all of the other pipeline will reside into the CrowdStrike cloud. Don't worry, it's secured over VPN, so we thoroughly tested this. So we have a generator service who has the purpose, like I said, of multiplexing the request that is coming from the Crowdy API. And we also have the indexer service that will be responsible for storing data into Elasticsearch. For exploring purposes, we're going to use Kibana. Okay, so what we're going to do into the next sections, we're going to deep dive into each of these components and see the interactions. And like I said, if you have any questions, please feel free to ask them, and we got swag. So then, back to you.
Thank you. So let's look at the first service. So our main entry point for the service is Crowd API. Crowd API, as Cezar already mentioned, is CRD, so create, read, and delete movies endpoint. Delete movies endpoint is disabled to please the demo gods, so sorry for that in case you try to access it. Then the second one, which is important, is the event generation. You can submit an event generation, which is essentially a job that triggers automatic event generation. You can control the rate, the duration of a job, and some other parameters like minimum and maximum rating, which would be randomly allocated for a movie. Why we do it? Of course, to generate really big amount of data we can process live as a stream to ingest in our pipeline and then view those in our system in Grafana for services metrics and in Kibana and Elasticsearch for our data visualization. To store the movies for CRD, we use a Postgres DB, which is used for only the movie storage. Event requests are not stored there. So now, to check out the Swagger API, you can log into the public Wi-Fi CCC WASPETS. It has no password on it. And then you need to access this URL. It's 192.168.0.162, port 8001/API/API-docs. We'll wait a little bit on this one in case if someone else has any questions. At the demo session, we'll share it again when we'll do a little bit of live generation and we'll review how our system works with it. So any questions right now? We mentioned we have swag for those who are active, so please engage. Okay, let's go ahead. We'll be back at the demo session with this. So our next service is generating rating service. What it basically does, it has a Kafka topic with our generation requests. The amount of a request, generation requests, are built manually by you here by submitting HTTP requests. So of course it's not that big of a volume, so we need really a small topic. What happens huge here is that in this service, we have distributed workers, which will take each of these requests and will generate random amount of, actually fixed amount, considering the configuration, amount of documents to be indexed by the indexing service, and will publish it to a dedicated Kafka topic. And of course, we are using a Redis, as Cezar already mentioned in the architecture, in order to progress tracking. If a person wants to know when the job was submitted, when it started to be processed, if it finished okay, or if it finished with an issue or an error, and so on. And of course, some of you may ask, what happens if this processing fails? In this case, we need a dead letter queue, a replay, a retryer, and we'll talk about it later in a separate slide, how we implement dead letter queue in our infrastructure and why we choose this approach, but of course later after we review the other services as well. So now back to Cezar to review the indexing service.
Awesome, thanks Dan. So, like you said, mostly we're going to store time series-like data. So the architecture that you see here is going to be a hot and cold storage. It's a bit forced just for demo purposes. In a real use case scenario, you're mostly interested on the overall rating. So if you go to IMDb or other websites, you actually get an overall rating. But we're forcing things a bit here, so we're making this architectural assumption here that we may have use cases where customers may be interested with data that's actually being stored within the most recent data. So that's why we basically have the split between hot storage, where we're basically using dedicated partitions. So each new day is written into a dedicated index, and we have a rollover policy, meaning that older data is being deleted. So each time we hit with a query, we're limiting ourselves only to a particular number of days. We also keep a cold storage, which can be another dedicated cluster. So also this architecture allows us to have different hardware configurations for each of these clusters, so that we can fine-tune and optimize the queries that we're actually performing. That's why, for instance, in a cold storage, if we have use cases or queries that we are interested in the entire data set, also the removed indices will be stored in the cold storage. So running an aggregation on the cold storage is actually going to have much more impact on the user, and essentially the query is going to run slower. But again, we're going to think also of ideas of how we can actually improve this side. So mostly we're starting from the read side, but we're here on the indexing side. So writing the data, how we've done this is that we had two different Kafka consumers. So we're using a batched Kafka consumer, which opposed to the generator service that Dan mentioned earlier, which was a more stream-like approach. Here, essentially, we're consuming batches of messages until either we end up having a fixed number of messages into a buffer, or until a certain timeout is met. Okay, so why do we have two different Kafka consumers? Actually, this is a question for you. So do you know why we're using two different Kafka consumers and we're not indexing data from the same Kafka handler, essentially? Okay, so the idea is that we're making an assumption here. Customers are mostly interested in hot data. So that's why we don't want to also handle the cold data into the same Kafka handler. So that's why we're using two different Kafka consumer groups. This means that the messages that are coming into the indexer service are replicated between each consumer, so we can scale the hot storage consumer with a higher priority. So imagine that you don't have the hardware capabilities of storing the entire data, so you store all this into a single Elasticsearch cluster. So having two different consumers, you can scale the cold consumer with fewer workers. So you're going to have an increased lag on that consumer, but you're having the hot data into your cluster and you can feed queries for your consumers, given the fact that you're actually making the assumption that they're interested only for the hot data. For our demo, both the hot and cold consumers are configured the same, and we're gonna see this into the lag that's actually being consumed from the services. Okay. Okay, so it's also well known, especially for the folks who had experience with Elasticsearch, we're using bulk Elasticsearch operations. Elasticsearch copes very well with these types of operations. So essentially each batch message is transformed into a bulk Elasticsearch operation. Yes, and like I said earlier, queries and aggregations are going to hit all the indices via a unique alias. And this is actually going to pose an interesting problem for us. Okay, so let's go further. Okay, Dan mentioned something about the dead letter queue. Okay, what this is, I think that someone from the audience, did you know what a dead letter queue is?
I say something like when you have messages in Kafka which can't be processed automatically and you need to intervene manually on the dead letter queue, I think.
Okay, exactly. So it's actually a failover mechanism, as we would use the buzzwords. Yeah, so imagine that you're having a Kafka consumer that's doing some processing, right? So at some point, he isn't able to process that message. So he's going to add have a retry capability. You can also add like an exponential retryer, right? Have it try double the amount of time you wait for that operation to finish. But imagine you're using a database, not necessarily Elasticsearch, and the operation times out. So what you do in this use case, because you still want to process that message. Indeed, you have a separate Kafka topic or a different queue. Maybe you're using RabbitMQ. So what you're doing, you're essentially forwarding the same message on that redrive topic so that you're consuming it later and maybe having the same configuration, like have a different consumer group that actually subscribes to this topic and consumes it in a more throttled manner. So you're having the same logic here as well, and you're trying to reprocess the same message again, right? But you can also end up having the same issue because maybe someone from the data services team didn't actually fix the issue with the database. So you still don't want to lose that message. What are you going to do? Okay, we have a large object store. Again, this is something that's completely agnostic because we're using AWS as an infrastructure layer. That's going to be an S3 bucket. But if you're using Google, then you're probably going to use some other object storage technology. Right, so we're failing on the redrive topic, but then eventually we're putting the message for a later on processing in the large object store. And eventually you're having alerts that are telling your system that the database is down, the database team intervenes, they fix the issue, probably they swap disks, so everything is working. And what we're doing right now is that you're actually replaying the messages that you stored in the large object store, and you're putting them back into the redrive topic. So this way you ensure that you're still processing the data that you previously managed, you didn't manage to process and store into your database. Okay, so this is a dead letter queue. Do you have any questions regarding this? Okay.
What is the difference between just not progressing with the processing of messages and
So
this
not
approach?
not committing the offset?
Yes.
The problem is that you're essentially losing that processing, right? That bit of information. Because if you're committing that offset, you're basically using that bit of information.
So you've mentioned you have a problem with the database, so
Yeah,
you cannot store, or
Yeah,
you cannot
yeah.
process and store the
Yeah,
event.
exactly.
So in this case then, if you're just rerouting the messages through the large object store and then replaying them,
Okay, I see your point.
aren't you actually ending up just with the same situation in which you would not advance in the processing of messages in the first place?
Exactly. I mean, the idea is that you would essentially end up having the entire live stream ending up in the data.
Yes,
Okay.
that's my question.
One thing you can actually do here is that you can add an alert that you're having a lot of these operations, right? So what you can do then, because you're dumping data into your database, you can scale this consumer group to 0, right? You can do this manually, or you can have like someone mentioned about horizontal pod auto scaling. Maybe you can have something like that that's based on the Kafka timeout handler. So if that exceeds or has a certain metric, you can also configure horizontal pod auto scaling to account the metric. You can downsize your indexer service so that you have time to fix the database. This can also be some external dependency. Imagine that you need to also enrich the data that you're storing from some other service. So that service can also be down and you're still ending up with the same issue. Right. I hope this answers your question.
Thank you.
Thank you. Okay, any other questions? Okay, I think we can move further. Okay, so I think it's the most interesting time right now. It's time for the demo. So then, let's hope this works.
Yeah, here we have the IP again for those of you who had no time to connect it. It's 192.168.0.162 at port 8001/API/API-docs. Sorry for the long URL. Basically, what we have here is a Swagger page with all the endpoints we are exposing. Let's look right now in our queries endpoints. We can query it for our movies. We have only 20 movies in the database. It's intentionally because we don't need a lot of them. What we want to test is the processing of the scale of the stream of the data. Just a moment. Okay, it worked. My Mac went to sleep. So we have our IDs here of our movies. Let's go up and actually get the movies from the database to see what movies we have. Let's take 3 from the middle. I'll take this one. Sorry, not that confident in this position to do a demo. I'll try to be as fast as I can. So we said we'll bring 3 of them. We'll take you can also submit requests, use your mobile or anything else by going to the same URL. The problem is we are using UUIDs in order to ensure uniqueness, so it's not that readable of IDs. So I pick 3 random movies. First of them is The Godfather, Inception, and John Wick. let's get and pick the Godfather. For each movie, as you can see, we have a name, ID, description, and actors. We included the actors and description in order to be able to search better or perform other queries later to show how our mechanism works, how our system works. So now by copying the first ID, which is the Godfather, we're going to make a request and generate, we have an endpoint to publish generate event requests. What we'll do here is we place the movie ID, we'll choose a rate which should be up to 1,000. It refers to 1,000 of publishes per second, which is multiplied by a number of workers we have there. We can submit it to run for 2 minutes. And we can have limitations for our rating. Let's say we want it to be between 3 and 5. Every time it will pick a random one. We're publishing our job request. Yeah, something happened. It's a course issue. No, actually it worked this morning, so.
Can we try that in the command line?
Okay, I'll try it again. Okay, it worked now. I think it's a networking issue. We are overwhelming the local request. What we get here is a job ID, which we then can see, but will start to generate our data. So we go back to our Grafana board with the data from our last 3 hours. One mention is that it's updating every 60 seconds. So we'll see a little bit of delay until the data starts to pop in. We can see there are other generator jobs as well for films like Green Mile, Spider-Man, and Shawshank Redemption. I'll pass the microphone to Cezar now to present.
Sure, thanks, Dan. So as you can see, the generator lag started increasing. Like Dan said, here we're essentially doing like a histogram, basically on the movies that we're generating. You can also see that we have some generation requests that have occurred. What do we have here? Here we have the number of messages that were received by the generator. It's also the overall duration. So we should see the time, the 2-minute window that Dan also selected for the test. This is the overall consumer status. It's essentially a value that's pulled from Graphite. I've mentioned earlier that we're switching to Prometheus. So if we scroll down a bit, we can also see the consumer status for the indexer. Okay, here. Okay, so what that does, it evaluates that consumer status that we're reporting to a technology that's called Borrow. Essentially, that's what we're using in integrating for determining the log and other Kafka-related statuses. It's a technology that's been developed by LinkedIn. Okay, and we can also see that the Elasticsearch operations are starting to increase. The log is also increasing on the indexer side, so you can see because the hot and cold consumers are configured the same. Essentially, the way that the lag is being consumed is quite similar since they have similar configurations. If we scroll down to see some metrics regarding CPU, okay, probably this may be related to the fact that this is something that Kafka is designed this way. You have a number of partitions for each Kafka topic, and those are allocated per consumer group. So this means that probably we have produced the single message with a single key. So this means that all the indexing requests are ending up on the same machine. So this means that only one of the CPU spikes this way. Here at 12:30, I've actually ran a demo, and I'm not producing with key. So this means that the indexing messages are being distributed across both Kafka consumers. And yeah, basically we're using two different pods, like you can see from this dashboard. Okay, so this happens on the generator and on the indexing side. So do you have any questions so far? Because I would like us further to explore the Kibana dashboards that we have created for these indices. Okay, so yeah, well, we have created some dashboards. So first of all, it's the movie rating. So yeah, we can see, for instance, the Avengers have a movie rating of, can you scroll with that mouse over there? So they should have like 4.499. Then we have Inception, which was a pretty good movie, but somehow it only has 2.6. Okay, the high performers are John Wick, Joker with 4.5 each, Saving Private Ryan, okay, seems also it has 4.5, and of course Shawshank Redemption. Yeah, I think that's #1 in IMDb, right? So I think it's a pretty good movie, right? Okay, so now here we can see the distribution per number of votes for each of these movies. Spider-Man has quite a lot of ratings. Okay, also Matrix. I think this was one of the first movies that we entered, so it's 7 million votes. Okay, what do we have here? Also Interstellar seems to have quite a lot of ratings. Now, I can tell you that these numbers are inaccurate. Can someone please tell me why these numbers are inaccurate? Why might this be an issue, actually? There's a problem with these numbers. They don't reflect the actual reality, especially these ones here. This should be the same because it's an average. If we remember what we're doing. Okay, we have someone from the audience.
Hot storage only?
So, the way that we pull data, you're correct. You're on the right path. The fact is that essentially we've configured Kibana. So the way you do this is that you're using an alias, right? So we're using the alias over both hot and cold indices, right? So this means that we're doing these aggregations for both on the hot data set and on the cold data set. Now, the fact is that the data is duplicated between the two indices, right? So this means that the actual numbers here should be half, right? Because that's a limitation that's imposed by Kibana. So a proper solution would be for us to also develop an API that was supposed to run the queries only on the hot indices, and eventually, like we discussed initially, eventually hit the cold indices as well. Right, so this was the first one of the major issues actually with our approach. Okay, also here we have rating submissions. This is a breakdown per each time range. Yeah, I'm not sure how relevant it is right now. We can also do queries on the data set. So if we change the tab, okay. Again, we're using the read alias, which is actually hitting again all the indices, which again, it's not a correct approach. So what we're doing now is we're determining the movies in which Keanu Reeves starred. So again, it's a query, it's an aggregation query with a filter, with a query term. So hopefully running it. Yeah, definitely Keanu Reeves didn't start in Spider-Man and Interstellar, but he did play in Matrix Reloaded, so at least we got one right. Okay, so do you guys want to run some other queries on the data set? Okay, so I think we can move further. Yeah, we should return to the presentation right now. So since we've seen the demo, how the actual application works, we're gonna see why did we choose Go. And then he's going to explain us why Go is a choice for us and also for the microservices that we have in CrowdStrike, which, by the way, we changed Scala for Go, so let's see why.
First of all, sorry for the endpoint. The Redis instance was down, so you can't retrieve the status properly. I saw a couple of you actually tried it according to the logs of the service. But Go service actually have not failed us, so we are going to review why we choose Go and why we love Go at CrowdStrike. As Cezar mentioned, we migrated to Go from other languages. And one of the first things that's very important in Go is the Go routines. You can think of Go routines as small, really efficient threads. But what Go does in the backend, it actually has a thread pool, which is usually equal to the number of the CPUs of a machine or the pod it's running on. And it's scheduling those small Go routines to be executed inside those threads. It has a proprietary scheduler, and it does a lot of less CPU context switching for those. So it optimizes a lot the runtime. It ensures the proper memory sharing and reusage of a memory for those Go routines. And in the time we found out, it really helps us a lot to work with them. We have a lot of synchronization primitives. One of the good things about Go is that it was thinked about cloud native, cloud first, distributed first during its design. And one of the most important primitives for synchronization we have here are the channels. You can imagine of a channels as a pipe, for example, where you can publish messages. Those are basically some buffers. In the default option, we have a buffer of one element, which is blocking on both sides. If a sender tries to publish something to the buffer, it has only one message. So if it's not consumed, it remains there as a structure. In case if receiver waits for something to be executed, it simply waits for a message to be published in order to get it to be executed. Now, the great thing is we can have buffer channels with multiple publishers and multiple consumers from those one without having any mutexes around this work around this job. So what we have in the second one is we have a lot of senders, a buffer with a configurable size. Let's say, for example, we want 100 of messages to be able to be published here. When buffer is full, sender is again blocked in order to not spam it and to not process, for example, those senders can be some Go routines consuming from a Kafka topic. And on the receiver side, we have inside the same process some other processors for those messages. And in case if there's nothing here, it can block and wait for it to be actually published and executed. Also, we have a lot of other synchronization primitives built in the default library. It includes mutexes, read-write logs, semaphores, thread-safe maps. And one important thing that is mentioned together with a Go is that concurrency is not parallelism. We must understand that in case if we have concurrency, so we have a lot of mutexes in our applications, we can say we are really using our system. We have a lot of context switching. We have a lot of I/O weight on the CPU. So what we want actually is to have a flow where we process a lot of the data. We use all the CPU. We see all the time 100% of the CPU usage without actually enforcing the CPU on the concurrency threads. Of course, Go supports concurrency as well in case if business decisions requires us, but you can model your service in order to not rely on this and be actually parallel and execute everything in a flow that's not blocking for anything. So we're going to share some code snippets. Don't try to understand or try to replicate those. We're just going to highlight how how much we like Go, and it's easy to understand. For example, this is one of the default, let's say, or recommended libraries to build RESTful APIs. Everything you need to do in order to generate the Swagger, to document your endpoints, and to actually link everything from your APIs is to define these sections of blocks. For example, in this case, we register an endpoint to the entities movie version 1 to create a movie. We say to this root what would be the function which will handle the request and will write the response. We say what are the data that actually would be provided, and what is the potential responses together with the statuses and so on. So you can generate a really big and full Swagger definition, which can be then provided to other, for example, UI engineers that can ingest it and create their clients from the Swagger definition. You can also do it in a CI/CD pipeline together with the UI team if you want to update it on the go when you add a new endpoint. Another good example, let's look at how we bootstrap a service, how a service is actually created in the Go. We just need to define a structure which is very configurable. So we declare our service. We enhance it with a lot of information. In our case, if we have a producer information, we need to init the Kafka producer with its configuration, which is coming from another part. We can also enhance here the Redis in our example and all of our services, and set up those on the service instance, on the service structure. And at the end, we return the service, which can implement some of interfaces. There are a lot of libraries which allows it, and you just call service start, and it starts everything, including consumers, API, listeners, everything that's actually needed. And here's another example with a generator logic. This is one of the examples where we use parallelism a lot and not concurrency. We have a context enrichment. So what we want to do, as you saw in our job, we want to execute generation with a deadline. So we have 120 seconds. What we do is we actually create a context and add this timeout to this context. Of course, until we start the execution, we'll have a couple of nanoseconds last here, but it's not the most important part. And what we do here with a Go directive, we are starting a Go routine, which we told was one of the great things here. And in this Go routine, we'll say until the context will actually be canceled, until the timeout actually reaches us, we should wait for the limiter. So we should make sure we have limit availability to produce a message and produce it on the Kafka topic. And one important thing is also the defer directive, which says when you'll finish this work, no matter if it's an error or anything else, you should define the wait group, another synchronization primitive, that it completed the work. And in the main thread, in the main routine we are executing, we're just waiting for all the routines to finish their work. After the timeout expires, after they generated everything, we're just waiting for them. So this is the full code that actually does the generation in the backend, and we have one function that does the randomization. You can see it somewhere here to generate the randomized message or to publish it to Elasticsearch or to consume it from Kafka and so on.
I have a question for the audience. So what synchronization primitive do you think that the wait group is actually having similarities with? Or how would you implement it? Okay, maybe this was defined at some point. There are very abstract primitives. It's a barrier because you're starting all those Go routines and then you're effectively waiting for all of them to complete the work. Also, one thing really nice about the context cancellation and with timeout is that it actually returns a channel, because we said we're using channels, so it's actually reading from a channel. Now, the fact that the for loop ends is that the mechanism in the Go runtime, which is responsible for dealing with context, will actually close the channel. So whenever a channel is closed, you get a message on that particular channel signaling to the Go routine that the channel was eventually closed, so you can add some custom logic. And in our case was essentially ending the loop for the data generation effectively. Okay, so now for the last part of our presentation, we're actually going to debate some of the limitations that we have. So starting with the generator service, we can see like, we can scroll all of them. Okay, so probably some of you have thought about this. One small issue with the generator service is that it consumes messages from the Kafka topic, right? But imagine that at some point you have to do a deployment. And you can't actually control when someone is submitting requests on the Kafka topic, right? And you might have in-flight jobs, right? So the problem with this is that you haven't committed the Kafka offset. So this essentially means that when you're restarting your service, you're gonna reprocess the same message again. And what this in fact ends up into generating the same messages twice. Now, one way to do this is that you can add some progress tracking. Within the progress tracking logic, you can also add snapshot times when you so that you can track the effective execution of your job. Of course, you can end up with clock skews because essentially you're just storing a time that was computed on that particular machine. But again, if you're accounting that time and computing the remaining time, essentially, it's only a matter of probably milliseconds or nanoseconds that you're still gonna generate data. So that would be a somewhat distributed known limitation, and given the fact we're not actually dealing with accurate numbers, that may be accepted. Another issue is that our current Kafka handlers that were actually handling the data can only have a limited timeout. So imagine if someone is actually trying to submit a request that has like 1 hour. Right now, the support is not going to work because that same Kafka handler is actually going to do continuous timeouts. So what we actually need to do is like have another dedicated topic so that we can replay the same generation request, basically, so that we're keeping the same progress on the same Kafka topic. So we're doing incremental data generation for the 2-hour or whatever long-running job system. So it's kind of a long-running job system based on Kafka. Okay, and also there was something else that someone said about horizontal pod autoscaling. As we've seen in the dashboards, most of the times the indexer was doing no work. So we provisioned 2 dedicated pods, and this means resource allocation and other services may not benefit from the rest of the resources that we have in the pool. So considering HPA is definitely something we should account for both services actually, because they're interconnected. Okay, now on the indexer side, we've highlighted this before. So the entire data set is actually being created at the same time. So this is kind of a limitation because we're not benefiting from the partitioning as sharding strategy that we selected. So that's why we should consider adding a dedicated API. You can also see here some of the further enhancements that we want to add. So only limiting and targeting certain queries only for the hot data, and if gradually moving to the colder data might be another solution. Okay, something else, maybe the fact that Elasticsearch can be under heavy load. So we can do this by essentially adding a throttling mechanism so that when you deal with the surge in traffic, you can actually have lag increased so that you will eventually consume. But the overall idea is that you maintain Elasticsearch health and your APIs are able to return data to your customers, and this is very important because you have the eventual consistency from the CAP theorem. You're eventually having the data consistent and you're ensuring availability for your users. Okay, so this pretty much sums our workshop. I think we also have, okay, we have the conclusion slide. Yeah, so especially when dealing with data intensive application, it's really important to start from the read path. I'm not sure which one of you is also familiar with Cassandra or has worked with Cassandra. Okay. You know, in Cassandra, you have to start with the read model so that you can then eventually model the write path. because you're configuring your clustering key and partition key based on your read patterns. So then eventually you can end up having the right model based on your reads. So that's pretty much what we did with our application. So we started thinking more thoroughly about having this time series-like data. So then we had the idea, okay, we have this huge amount of data. We can partition the data based on hot and cold storage. We need to run aggregations and queries, so Elasticsearch is definitely a good technology for this. Also, MongoDB may fit the same use case. So having the read patterns and read path defined, we can easily model the indexing side and then leverage and also use the Kafka mechanisms to do throttling and other mechanisms to protect Elasticsearch and not for different spike variations. So yeah, and of course, we've seen the dead letter queue pattern, which is something really extensively used in cloud systems. So you should also try to consider using this as well, because this is not something technology specific and can be easily implemented in any microservice. Okay, so that's pretty much it. Okay. If you guys have any questions, also please feel free to engage with us at the booth. We also have other swag to give away, and yeah, if you're interested more about Go, we can deep dive into the code. Like you've seen, the content has been pretty a lot, and yeah, thank you for, I know it's lunchtime, so enjoy your meal, and yeah, if you have any questions.
I'm sorry that it's during the break lunch. How would you handle GDPR in Elasticsearch? I mean, do you have to rebuild all the indexes, or can you share some tips, tricks, how to do it faster without waiting for all the data to be rebuilt?
Can we try it both? I mean, you can have, that depends where you can have like, we do have actually this approach in CrowdStrike where you're actually partitioning dedicated clusters per certain customer. So imagine you have sensors that are coming from the EU. You can have a dedicated cluster that only deals with those customers. And then when you're doing an API query, you can use a specific key that you're also using when routing the data, so that only the EU users are able to query that Elasticsearch cluster dedicated per EU. Dan,
Yeah,
I think.
that's it. But dedicated pipeline, the full pipeline. Sorry, the full pipeline is actually replicated in multiple clouds in order to handle the GDPR or other regulations or other complaints situations. So we can have dedicated flow, which is stored only data centers, only in AWS in Europe, and so on. So in this case, we are not affected by this information. And also at CrowdStrike, we have two different concepts, customer data and non-customer data. For non-customer data, of course, it's not a problem. I saw there was another questions there.
Yeah, so if I'm not mistaken, at the beginning of the Go section, you mentioned that you transitioned from another language to Go. So I was really curious, how was that like?
Cezar, do you want to take this one?
To be honest, we are too young for this question. No, actually a colleague of mine did the transition from the Scala microservice to the Go microservice. It was an eventual migration, right? So at some point, new microservices started being written in Go, but older microservices, legacy microservices, started being migrated and ensuring that you have the same functionality, essentially, right? Because you don't want to lose functionality. Yeah, and other than that, I mean, we had an API that had essentially to be migrated. It's a pretty known technique, this. It's called shadow testing. It's a paper that AWS had written. So what we essentially did and ensured that we have the same results, right? You're having a different microservice, it has a different output. You're essentially running the query against the new microservice, which is less scale, and you have a small percentage of your queries that are hitting that. And for that number of queries, you're also doing from your service, you're instrumenting code and you're hitting the Scala microservice and you're comparing the output. And then you can add like dashboards to see, okay, this is the difference between the two services. So this was one technique. Other questions?
Yes, I have a question. Why Go and not Rust? Rust is faster, and actually Scala is better in terms of microservices than Go. And
Yeah. If you ever saw the Scala documentation, it says a lot why this language is complicated to learn. With Go, we achieved the thing that any developer that joins the team, he can become or she can become proficient in very fast time. Go learning curve is one of the smallest probably from all the languages. And why not Rust? I think it's more due to the fact that Rust was not that mature at the point we chosen Go. We have our services actually running Rust. As we mentioned, we have exceptions from everything. Our machine learning pipelines are usually using Rust for training and inferencing for the speed and so on. So it's kind of a question of a preference, but if a technical problem requires to use Rust, for example, for memory safety, because you don't want to have a garbage collector, which you have in case of Go, we can go with Rust and we do it if it's a requirement. So it's just a default solution is Go, but you every time can go with something else.
I also have another question. Since you mentioned, so what kind of machine learning services you have?
What do you mean by machine learning services?
I mean, for what do you use machine learning?
Okay.
And let's say, what kind of models? Very generally, not.
I think that's a question for machine learning team and applied machine learning team, but we use machine learning a lot, as mentioned. We have a lot of different models for different patterns identification, for example, behavioral identification, for file scanning and so on, which are running some of them on the cloud side, most of them on the cloud side. So in case if something happens on the customer's machine, all the events are submitted, and those events are actually analyzed by the model in order to determine, for example, abnormal behavior of processes or some strange things that were previously seen and considered dangerous and were marked actually as dangerous. And we also have a couple of those models simplified a lot, like shrinked a lot to have smaller size and are running on the customer's node. So in case if, for example, you have a ransomware or something that cut the network, you still have models that can protect the endpoint without being exposed to the cloud. And we also have different models for research purposes, of course, which derives a lot of information from file analysis, from as well processing analysis, process tree analysis, and so on. It's a really big amount of models. They're replaced every couple of times. I can't enumerate all of them. But we can put you in charge if you are interested. We can connect you to some of our machine learning engineers, and you can discuss more on LinkedIn or any other platform. Any other questions?
At the start of the presentation, you said something like you want to switch from AWS to on-premise or some other, I don't know, cloud provider. So my question is why maybe you face some issues or with AWS or I don't know.
Yeah, so it may seem that most of the Kafka capabilities you can actually do with SQS, right? SQS and SNS, a combination of the two microservices. It all comes down to cost. We're ingesting 1 trillion of events per day. That's a lot, right? So imagine the costs in an AWS setup for that. It's a lot. So we're moving most of the workloads that we're having for Kafka that are so Kafka, Elasticsearch, and other databases are managed by us. We don't use nothing managed by AWS or something, right? So even if we have the deployment in AWS in EC2 instances, we have a dedicated team that starts a JVM process and then uses a certain configuration for that. Now, having this approach will enable us to transition easily if we say we don't want to use AWS anymore because they have like very huge costs, and then we can move easily to Google or other cloud provider, right, that offers us this better alternative, right? Okay, so I guess this concludes the session. Thank you.